If you remember this is our graphic syllabus from the very first day of class, where we kind of laid out the plan for the whole semester. It took a look at what's needed from you, some prerequisites between algebra to pre-calculus to trig and calculus. And then it went over these topics that we were going to do. So we did vector functions, we did the velocity, acceleration, and motion stuff of vectors. We just did the multivariable functions. And once we got introduced to that, we immediately jumped into finding directional derivatives and gradients. And then we did double and triple integrals. So those are the things that we've accomplished so far. Now we are into this idea of taking derivatives and integrals of a new kind of object. So the new kinds of objects that we dealt with were vector functions, basically parametric equations, and then we took derivatives and integrals of those. And then we went into F, going from R2 to R, those types of functions. And then we did partial derivatives, directional derivatives, and gradients of those, and then the triple, double, and triple integrals of those. So now we are going into a new kind of function to deal with. They are these things called vector fields. And then normally when you study something in the order of calculus, you would find derivatives and then integrals, but we're going to immediately jump into integrals, and then we'll backtrack and take a look at derivatives of these vector fields. So that's what we're going to do, is vector fields. And once we start doing vector fields, we're going to start tying things to gradients. We're going to tie things to multiple integrals. And these vector fields have, the word vector in them, so there's going to be some vector stuff in there. But when we start tying those things together, we're going to refer to them as the fundamental theorem of calculus. And we'll see them as different things. There are different theorems throughout this chapter. But in the end, we're going to hope to wrap it up into one big fundamental theorem of calculus idea, where the integral of a derivative is the original function evaluated at the boundaries. Now those words will be varied a little bit from theorem to theorem, but we're hoping that it'll all kind of tie in and make sense, or all tie in. Maybe it'll make sense. Okay, vector fields. So today we're going to talk about vector fields, and then we're going to sneak in the first type of calculus that we're going to do on those vector fields, which is line integrals. Also gradient fields. So that's our plan for today. So vector fields. A vector field, let's start off by doing a notation. A vector field is a function that we'll generally denote as capital F. Now, since it is a vector value in the end, or as an output, we put an arrow on top. So in the book it's bold-faced, and for us we'll put arrows on top. And what this does, in our first glimpse of it, we'll look at it as taking a two-dimensional point and then assigning to it a two-dimensional vector. So we can think about this as taking a point in 2D, and then we're going to output a vector in 2 dimensions. So you're going to have to really be careful in reading notes up on the screen or the textbook or problems that you might see. You want to be careful to identify when something is a vector versus when something is a scalar. My R here looks. When something is a scalar. And those account for functions as well. So in general, what we have here is an xy point. And then now the vector that you would come out with is going to be a vector that's dependent on the xy point. And so the vector has 2 components, since we're talking about something in R2. So we think about that as some function that takes in the x and y values that you have for your input. And then, well, there's 2 slots, so we probably should be looking at identifying 2 functions that take in that point x, y. And then in 3 dimensions, we just imagine it going to 3D. So instead of having a 2-dimensional point and a 2-dimensional vector output, you would get a 3-dimensional point, and then you get a 3-dimensional output. Okay? So usually the first thing we want to do when we are studying new types of functions is to look at them numerically and graphically, and then figure out what to do with them symbolically. So let's do an example. This is probably the most popular first example for vector fields, and so I'm going to go with this also. Negative y, comma x, and sometimes you'll see it negative y, see it written with the I and j components, and so you just have to be able to read it either way. This is a y, not a j. And this is a j. So this would be a typical type of function. Now, if we want to look at this numerically, when we first started to learn functions back in algebra, we would take a look at the function, and we know that it takes an input and an output, so we would make a little table and put values in. So it's kind of natural to do something like that for a new function that we're dealing with. So let's say our input would be just any ordered pair that we would select, and there's, it's hard enough thinking of when you put in an x, you get a y. You think about which values of x you put in now, you're going to have to figure out which values of points, pairs you put in. And then what you would get is the output. And so you can say y, or you can't say y, but you can just rewrite that function down here if you want. And then you put in values for your input, like maybe a 0.00, which in this case is going to be 0, 0. So it doesn't really give you any new piece of information. But that's the general idea. It's a function, so there's an input, there's an output, and you can make a table. So more interesting, let's put 1, 0. And then that would give us an output of y is 0, so that's going to be negative 0. And then x is the second component, that'll give you 1. And then we'll take a few more samplings of things, like maybe 1, 1. So the y is negative 1, the x is 1, or the y is 1 with a negative in front. And then 0, 1. So this time it's negative y. Y is equal to 1, so that's negative 1, comma, and then the x is 0. Okay, we'll pause here and take a look at the graph. And then we'll see if we can decide to add anything else here. But graphically, how's it going to look like? Well, 0, 0 is not going to give us anything interesting. It's going to give us 0, 0. Now, if I take a look at the point 1, 0, add the point 1, 0 there. The output is 0, comma 1. Now, 0, comma 1 is a vector that would point in the positive direction and in the y direction. So I'm going to draw a line here, but you don't have to do it because I'm going to end up moving it. Maybe a little bit longer. So the idea is that I have a vector. This is a vector 0, 1. Well, that's nice. Except now that it's a vector 0, 1 sitting at the origin, I don't know if it makes too much sense for me to deal with this very well. So I'm going to take another point, like 1, 1. And then I'm going to see where that vector 1, 1 is going to go. So the vector 1, 1 is going to get sent to negative 1, comma 1. So negative 1, comma 1 points this way, I think. So again, it doesn't help me too much. And then let me put one more here. Well, the point 0, comma 1 is this. This is the point 0, comma 1. And then the associated vector with that as an output is negative 1, 0. So negative 1, and negative 1, 0 goes like this, I think. All right, so those 3 points and then the 3 vectors don't really make sense if they just leave it looking like this. But so here's the thing about graphical representations of vector fields. What we want to do with these vector fields is that the output, which is a vector, should go and be placed. Remember, vectors have direction and magnitude, and it doesn't matter where they start as long as they have the same direction and magnitude. It's the same vector. So I think it would make a lot more sense if we put these vectors, if we put the tails of those vectors where instead of sitting them at the origin, we put them at the actual point that was their given input. So if I take these vectors, these 3 vectors, and put their tails where the point was supposed to be. Now, I think I have something that would make a little bit more sense in terms of trying to describe this field. Okay? Yes?
What did you say about the outputs again?
The outputs are vectors, and what we're going to do to try to look at it graphically is to put the tails of the vectors on the point that was their input. Tails of the so we're going to pick up the vector in standard position. They'd be at the origin. We're going to pick them up and put the tails of the vectors on the points that were their input. Okay? So if we go back and try a couple more, let's try this point, -1, positive 1. Their output is my y is going to be negative. So my y was 1, it's going to be the negative of that 1, and then my x is -1. So I imagine vector -1, -1 going down like this. So let's pick that up and put it over here. And then let's try another point like -1, (0). That would be 0, (-1). So 0, (-1), 0 in the x, -1 in the y. That would just be going straight down. And then we'll pick that up and move it over here. So you get a feel for this vector field a little bit. And then we could try something, we're going around. Looks like, can you see what's happening? It looks like we're going in a counterclockwise circle direction, right? And so let's try, if we try another one that's kind of further out. Like, I don't know, 2, 3. So the output is -3, 2. So 2, 1, 2, 3 is over here, and -3, that's negative in the x, positive in the y, so it'll probably be going up like this. So this is your point 2, 3, and this is your vector -3, 2. Okay? So notice now that the vector up here is a lot longer than these vectors over here. So it looks like the farther you go out, the longer it's going to be. And I know we look at vectors with length and magnitude. But in a lot of cases, not all, but in a lot of cases, when we're studying vector fields, it's more important to look at the flow of the vector field instead of the actual lengths of the vectors. Okay? So you have a lot of graphing programs. I don't know if the TI-89 does it, but the online graphing thing has information about that as well. This graphing calculator has a way to represent. Has a way to represent vector fields by writing it like this. So this is the vector field that we have, -y, x. And then if I ask it to graph, you see that it goes around in a counterclockwise direction. So the tricky part is that it's hard to see the components and see how long these vectors are, because the vector field, the graphing program has to adjust for the size of the vector. And so they talk about the component, how long it should be based on the input and output, but they don't show it graphically, because if they draw these vectors too large, then it's all just going to get kind of mixed up. But you can kind of tell there's smaller vectors at the closer to the origin and larger vectors as you go out. So you know that generally there's a change in the magnitude of the vectors. All right, so this is a good picture. Actually, red. The point is that you can ask some graphing program to draw the vector field for you so you can get an idea of what's going on. Okay? So that's a vector field. Now, what's interesting about, well, let's do another example of vector field. So our other example is this. Can you imagine what this vector field might look like? We could do the table again, but you can see that the table xy is going to be the same, right? So if you have 1, 0, you're going to get 1, 0. If you get 1, 1, you'll get 1, 1. Can you imagine how this is going to look like? Looks like it's just going to go outward kind of thing, right? So if we have a point here, it's going to go out this way. If you have a point here, it's going to go out that way. Point here, it's going to go out that way. At least these are the three that we have listed. And if you go further out, it'll be whatever the length of this is. Actually, this probably should be a little bit longer. So it looks like it's just going to be an outward vector, a vector field that goes outward. And if we put a minus sign in front of this whole thing, and it would just go inward, right? So it's good to get a feel for these. These two at least are, you know, your basic vector fields. And we can go to 3D. And in 3 dimensions, maybe we'll do something similar or do something a little bit different. But let's take a look at 3D. Okay, so this is a long-winded looking vector field. Let's take a look at this. Are things looking the same and looking different here? Yeah? The denominator is similar, x squared plus y squared plus z squared. That looks like a pretty special looking denominator too. What's different about these things, about each of the components? The what? a numerator is x and x in the x component, y in the y component, z in the z component, right? So try to imagine how this thing would look like in 3 dimensions. What do you picture? Yeah. So the x, y, z, if it was positive, if the negative sign wasn't there, the x, y, z would kind of like work the same way this was working. It would just go outward, right? But because it's negative, now it looks like it might be going inward. And I was going to ask about this business. This business looks like it makes it into a unit vector because that's just the magnitude of x, y, z. So if you imagine taking out a -1 over the square root of x squared plus y squared plus z squared, and then all you would have left after you take that out is x in the x component, y in the y component, and z in the z component. And if you take the magnitude of that, it is essentially this x, y, z. So the x, y, z is a vector field that goes from the center and goes outward. The negative makes it go inward, and then the denominator makes it all unit vectors. Is that cool, or is that like, don't get blown away yet, because there'll be other times where you're going to get blown away. So let's see if we can draw this out. So this is your denominator, and then you just have x, y, z. So if you just try to look at the arrows and see how they're pointing inward towards the origin. And then wherever you are, you'll have a vector going in towards the origin, and then it doesn't matter where you are, it's always going to have the same length. So that's nice. Any ideas what this might be used for? Forces in 3D. A what? Motion? Could be used for motion. What? Maybe navigation. Closer. Gravity. This looks like a gravitational field, right? Gravitational force. If you're the Earth, and we'll put a sphere here if we want, but let's say you're the Earth, you, and then so these arrows pointing downward, kind of pulling towards the center of the Earth. It's a gravitational field. This one over here is often looked at as an electric field. It goes around. So this is a two-dimensional representation, but if you had a rod in 3D, there's some fields that are going around the rod. And so magnetic fields maybe? I don't know. I forgot. I have to look that up. Anyways, so there are these fields that are existing in our real life situations that we're going to take a look at briefly, and then we'll do some math on it, some calculus on it. All right. So speaking of physics and engineering, sometimes they let r, the vector r, equal to x, y, z, because they deal a lot with electrical or with these gravitational fields. Sometimes they let the vector r be x, y, z, so that this thing can get replaced with r, and now the magnitude of r can also be replaced. So then your vector field now has a way, way easier notation to write, where the x, y, z, I mean, we can look at an x, y, z as a point or a vector, but we can just say, oh, that's just f of r, and that's equal to negative r over r squared. So the real gravitational field involves a couple of masses, the mass of the object that's bringing in the gravity, and then there's also going to be a mass of another object, m, that's going to be in a point somewhere in x, y, z, some gravitational constant, and then it turns out that the denominator is raised to the third power or something like that. So you can take a look at that example in your textbook, and I'm sure you'll do problems around that. But this would allow, this notation over here would allow for a slightly shorter hand notation. And like I said, this is how you'll probably see theorems in physics and other places. Okay? All right. So there is one type of, a special type of vector field that we're going to discuss today. Oh, here's a gravitational field. It looks something like this. All right, so let's take a look at a type of field called a gradient field. So if you have a vector field let's say it's equal to x and y. Now, if you can find a function, now note that this is a function that they're talking about that's a scalar function. If you can find a scalar function where the gradient of that scalar function, remember the gradient is just the derivative with respect to x and derivative with respect to y put into a vector form. If you can find a gradient, if you can find a scalar function whose gradient is equal to the vector field, then you have what's called a gradient field. Okay? So if we take this example, x comma y, can we think of a function of xy, a scalar function, not a vector, right, a scalar function, so that when we take the derivative, it's equal to this. We take the derivative, let me move this down a little bit. So that whatever function we have here, if we take the derivative of this with respect to x, we're going to get x, just x. If we take the derivative of this function with respect to y, we're just going to get y. So the question is, can you find a function like that we can put here? One half x squared plus 1/2 y squared. So if we check that, the gradient, remember, is taking a look at a scalar function and taking the derivative of that function with respect to x. And so you bring the 2 down, you just get x, and then this is 0. And then if we take the derivative with respect to y, we're just going to get y by itself. And so yes, it looks like it does work. So if you can find a function like that, then you can say that the original f that you have, xy, is a conservative vector field. And the function the scalar function is the potential. Yeah. Well, by definition, a potential function is a scalar function whose gradient is the vector field. So you begin with a vector field. This is your vector field. You begin with a vector field, and if you can find a gradient, if you can find a function whose gradient is equal to the vector field, then that function that you found is a potential function. Okay? Now, on the other hand, I think this will work, or this will not work. Can we find a function whose first derivative is equal to negative y with respect to x, and whose derivative with respect to y is equal to positive x? Any guesses? Well, it has to be a scalar function, so I can't have commas. So I can do this plus or minus or times or log or sine or cosine. Plus xy? Oh, this would be equal to 0, right? Yeah. So let's see, the gradient of this, the derivative of this with respect to x is negative y, the derivative of this with respect to y is negative x. Well, that's not the same. Another try. No. But we should try anyways. Oh, okay. I'll stop and say, no, we can't find such a function, so we have to conclude that this vector function, negative y comma x, or this vector field, is not conservative. And so because it's not conservative, we're not going to be able to find a potential function. Okay? All right, a little bit later on, we'll find a way to, without having to guess, because that's what we were doing. We're just guessing. Guess this one. Guess this one. Didn't work. Guess this one. Nobody wants to guess anymore. So we've just been guessing, right? Eventually, we'll find a more sound way of figuring out whether something is a conservative vector field or not. And when we do, we'll establish more ideas and theorems around conservative vector fields because they are kind of special. Okay? All right, there's one more idea here that I wanted to talk about called flow lines. And if you look at a vector field, I didn't write down the definition for a flow line. Yeah. Oh yeah, yeah. I mean, if we add 5 to this, or 7 plus c, yeah. So there's a glimpse of integrals here, right? Because if you had any random constant here, then the gradient's always going to look like this. So yeah, definitely. Maybe I should just have you guys look up flow lines on your own and see what you get. Yeah, you guys can worry about that. Okay, let's jump to the next. Oh, I don't have definitions. Ah, man, I didn't prepare. Oh well. Let's go into our next section, line integrals. Now, the book calls it line integrals, but I think I want to make a distinction between two types of integrals. Because I'd like to keep them separated because the form of the integral itself is different. So let's take a look at path integrals first. So we're going to let, what do they call it? They usually call it C, be a curve in R2. So it's going to be some sort of object, right? It's going to be a curve. How do we write curves, by the way? Or how do we express curves? Parametrically, right? Vector functions, parametric equations. So we're going to look at these and then change them into parametric equations. So C is some curve in R2. And then for path integrals, we're going to let f of x y be some function, a scalar function. So that means the input is a two-dimensional input, and then your output is a one-dimensional scalar. So we can write f of xy be a function that's defined and continuous and all those nice things. On a domain D that contains the curve C. Those are like the restrictions. So I'm going to see if I can draw a graph here. Now I know this is happening in 2 dimensions, but I want to take a look at this as a 3-dimensional object. Because the function is some function that's up on top here. So the domain D could be anything as long as it's just giving some sort of restrictions for the function. And the shape of D is not important. The shape of C is important. Then the path integral of f over c is given by, now we're going to integrate the function over c. Now the tricky part is that this is a one-dimensional integral, and we want to integrate the function over the curve c. Now the curve is not like an interval where it's just a straight line on an axis. Or it's not even like, you know, for double integrals, we took a look at a region where we made little partitions. So the partitions that we need to imagine here have to be with respect to the curve. And so that curve is dependent on, you know, how we partition it depends on the arc length of these things. So this is going to be with respect to arc length. Now, remember when I asked what kind of shape do we usually describe C, and then Evan said parametric equations, right? Do you remember how we used to write parametric equations in vector form? Yeah?
Yeah, there's like L vector or G, or like
It could be L vector, but R of T is what we're looking for. So what we need to do is we need to represent your vector parametrically with x of t and y of t, and then we usually call that r of t. So that r of t is going to be that arc length that we're looking at. And we talked about arc length before. So this time we're actually going to use that information in a lot more detail, and we're going to take a look at the arc length. Okay? Now, what are we getting out of this? If we break this up, because we have the function f of x involved here, right? If we imagine projecting this curve that's flat on the xy plane, and we project it up onto the surface, and so we can imagine maybe this goes along the surface up there. What are we actually finding? Well, if we break this down, we're integrating f with respect to these little pieces of arc length. Well, you can imagine, maybe I should have drew the function a little lower, but well, you can imagine there's maybe a fence whose height is dependent on the surface up on top, and then whose shape is dependent on the curve down below. And we're really finding the f function, the z function, z component, so that's the height, times the little arc length partition. So we can imagine this geometrically as finding the area of this fence whose shape is curved along C and whose height is kind of constrained by the function f. Okay? Is that okay? Yeah? Yeah. We can make it an infinite number of lines in order to make it into an integral. Yeah. Yeah, the distance between these things will be delta r, and then you make it smaller and smaller, it becomes a dr. Yeah. All right. Now this, computationally, is useless. So we want to know how we can actually find this path integral if we were given an actual problem. And so what happens is that we go into some sort of what I like to call a working definition. And the working definition will allow us to actually compute these path integrals. So we'll start off with the formula for a path integral. And then we're going to say that this is going to be equal to, well, we need to parameterize C. By this vector. And then when you parameterize C, you're going to need endpoints, a starting point and an ending point. Okay? So once you figure out the starting point and ending point of your parameterization, this path integral now becomes a basic single variable integral that we would have seen in Calc 2. Now your integrand is f that has an x and a y. But it looks like, based on what we have started over here, we have t values for a and t values for b, and the single integral would probably be a function of t. So what we're going to do is we're going to take our function x and y, x of t, y of t, and put that into the function f. So now it's a function of t. Now the other tricky part is that our dr is with respect to arc length. Do you remember the formula for arc length? Yeah? That's like that's probably for an arc of a circle, of a piece of a circle.
R prime theta, R prime theta squared plus R.
Close, yeah. So it's something with an r prime of theta. It's a square root of x prime of t squared plus y prime of t squared. But that can be actually compacted. So this is a square root of x prime squared plus y prime squared. And then that's our arc length portion when we're integrating with respect to arc length. Okay. So this is one of seven or eight integrals and integral types that we're going to need to know. And then one of the other things is that you need to make distinctions. You need to be able to distinguish between these different integrals. So the book calls this a line integral. Because it's kind of delivered in the line integral section. But I'd like for you to look at this right now and tell yourself that this is a path integral. And then the line integral is something that we're going to take a look at tomorrow. So let's see if we can do a quick example. Should we do an example from your homework or from your lab? Homework. Let's do the first one. So your f function is x times y. So your curve is t squared comma 2t. And then your a and b, your limits are going to be from 0 to 5. Oh, the other thing is they call it s. I'd like to call it r. Anyways. So if we want to break this up into the little pieces that we have, f of x, you don't have to do this, but I'll just put it in our notes. X, y, your r of t is equal to t squared comma 2t. And then this is your a and your b. Okay, so your integral is going to be equal to xy. So in place of x, I'm going to drop the whatever the t is, the x of t. So it's t squared and y is 2t. And then I need to, on the side, try to figure out my r of t, or r prime of t, which is 2t and 2, right? And I need to find the magnitude of that. Square root of 4t squared plus 4. And then I'm going to go from 0 to 5. Okay? So 0 to 5, I suppose I could simplify this. I can take out a 4, I could take out this 2. So there's a 2 times 2, t cubed over t squared plus 1 dt. And let's see if I can quickly do a Wolfram. Integral of t cubed times the square root of t squared plus 1 t goes from 0 to 5. So because of the r squared, or because of the arc length business, these integrals are usually going to have a square root of something that's not very nice looking in there. So a lot of times you'd probably want to get used to being able to punch stuff into Wolfram Alpha or even your own handheld calculator. Did they want the answer in let's see, 25581.3. Come on. 8 over 15 times 1 plus, this is ridiculous, 949 times the square root of 26. Right. Well, good thing you're going to have Wolfram Alpha or something to calculate stuff for you. Okay. Yeah, if I asked you to evaluate it. But remember last test I just asked you to set it up, right? So.